So I think this will answer your question.
No, I figured it out.
Okay, well, I'll answer it anyway. So as a review, we talked about circular motion. We said that if I am moving with a velocity v0 here, and we're moving at this point with what I'm going to call v final, but in reality v0 equals v final, but they're both vectors. We can write acceleration as the change in the velocity divided by time.
You understand that if you cut it lower in the chair, larger radius.
So this table has voted and has decided that they don't want me to lecture today.
We just missed a step, and Nicholas now.
Then you raise. I don't want to be disrespectful.
Yeah, none of us are trying to be that.
I don't want to be disrespectful, but I've asked you to be quiet, right? I just stood here and said you need to be quiet. I came over and you didn't get the hint. Right? And the last thing you want me to do is to say I'm not going to, maybe you do. Maybe you guys can figure this out. We have a test on Monday. Okay? Right? The last thing you want me to do is to say we're not going to, that you're on your own. Okay? The other option is to kick the three of you out. Right? So tell your respective coaches that you have to make the class up at the end of the day. Did that go over well? No, right? So I think we need to think about a different place for you guys to sit. Okay? Because this is a habit. So not to waste any more time. If I need to speak to the three of you again about talking, I would just ask you to go hang out in Heston's office, okay? Okay. So you have this situation where we've defined acceleration to be change in velocity over change in time. And if I do that vectorially, I can draw my final velocity, v final, and I can draw minus v0, and I get a vector that is in this direction. So that's v final minus v0, and it's directed inward. We spent some time on Tuesday, I guess, or Monday, talking about how we could get a value for this, right? By looking at how far it is around a circle, using the relationship that the sine of theta is equal to theta in radians for small angles. And we came up with the relationship that acceleration is v squared over r. Centripetal acceleration is v squared over r.
What's the largest angle you can use that principle for? Sine theta equals theta.
Um,
Like how big can you get?
5, 10 degrees is okay. 15, you're beginning to get a little sketchy. Actually, if you look at I think it's the binomial. Look at one of those expansions. You can see how that ends up working out. You know, back, a joke about this, but back in the old days, when we didn't have, calculators that did all this stuff for us. Yeah, so sine of theta is equal to theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial. Right? And that just goes, it's a infinite series.
Yeah.
So if you bring it out, if you think about it, get to, what the angle at which theta in radians over 3 factorial is smaller than that, then you're in good shape. So 5 works out great. Again, radians. 5 degrees in radians works out well. 10 degrees in radians is getting to be a little sketchy. 15 is. And in reality, this is why when we did the period of a pendulum, even that angle didn't matter. You'll see in the January, February, March timeframe that we actually use the fact that this sine and the angle are basically the same. And that will explain, that would be the physics behind why it doesn't matter, why angle doesn't matter. Yep.
Is that an alternating series or an approaching series?
I have no idea.
It's a Maclaurin series. You don't do it
So what?
It's called a Maclaurin series. You do it much later in the calculus.
But it alternates. Like,
It goes plus minus, yeah. But honestly, this is like, this falls into the category of, I did this like 45 years ago, and I just know that it's like, why does it work? Because I couldn't even begin to derive this. Okay, so there's another. So everybody, so the other option is that I look at my circle and I say that I'm moving through some angle in the circle, delta theta. And then I want to get a sense of how far I've gone on this circle. So what is the path length of that arc? And how do we get path length of an arc? I probably should have done this slightly differently. Leave that out. So I move through some arc length. How do I define this path length S? Yep.
Like S over.
No, you're 100%. You actually were just about ready to say what I was just about ready to write, and then I decided I would say it differently.
Okay.
No, you're great. You were going to say delta theta is S over R.
Yeah.
So I'll honor that and write that down. Is S over R, which gives us S is equal to R delta theta. Right? Okay, now, yeah. S is the arc length. S is the length of that arc. Delta theta is this angle right here. So if I take the derivative of both sides, I would get, I will say delta S over delta T is R d theta dt. Then I can say the rate at which my position on that arc changes is the same as tangential velocity, right? So this is v tangential. This is the radius. And we call this d theta dt omega. So now I have a relationship between how fast a point on the edge of the disk, so to speak, is moving, and something that we call angular velocity. And omega is measured in radians per second. I can use this relationship and write that centripetal acceleration, which is v squared over r, is also r squared omega squared over r. A sub c is r omega squared, and that's what you were thinking of. Yeah. Okay, so that's another formula, another way to solve the problem. The other piece that sometimes you just see problems asking you is to say, suppose you have, a disk rotates 3 revolutions per minute, 3 RPM. What is the angular velocity? So how many radians per second is it moving? So you would do, that there are 2 pi radians per revolution. And so you could say 3 revolutions per minute times 2 pi radians per revolution. And then you would say 1 minute is the same as 60 seconds. And if you do that all out, you end up with 6 pi radians per 60 seconds. 0.1 radians, pi radians per second. And then if I were to ask you how fast a point was moving, so if the disk is 15 centimeters in radius, then the velocity, the tangential velocity, would be omega times r, which would be 0.1 pi radians per second times 0.15 meters, and that would give you 0.015 centimeters per second. Is that clear? Okay. The one final point I want to make is that just when you thought you were happy with this idea of centripetal acceleration, so let's suppose I've got a constant velocity. What direction is the acceleration in? Anyway, right? So I've got a velocity in this direction. That's v sub tangential. That's a sub c. Suppose I now speed up. So suppose at this point right here, I also have a tangential acceleration. How would I get the magnitude of the total acceleration?
You would combine the vectors.
So I would say the magnitude of the, you're right.
Yeah, you take the magnitude of the acceleration would be the square root.
Right. So it would be the sum of the square root of the sum of the squares. So that would be a sub t squared plus a sub c squared. Right? Does that make sense? So if I'm going down a road, and let's suppose that at this point right here, my tangential velocity is in that direction, and my acceleration, I'm slowing down, is in that direction. What direction would the net acceleration be? Going down a road, I am turning, this way, but I'm slowing down. So what direction is my net acceleration in? So like, is it up and to the left, down and to the left, down and to the right, up and to the right? Yeah, what do you think?
Down to the left.
So I would have a centripetal acceleration in this direction, a tangential acceleration in this direction. So my net acceleration would be in that direction. And conversely, if I am still moving in that direction and I am now speeding up, what direction would my net acceleration be in?
Up and to the right.
So it'd be a combination of this vector and this vector. So it would look like my net vector, my net acceleration would be in that direction. Cool. What's today, the 25th?